Hey kids, welcome to Flip This Classroom 5.1c. Tonight, before we get started, I think it would be a good idea to go back to your toolbox and write in those various ways to factor. It'll be a good review from yesterday if we go ahead and talk about it at the beginning of tonight. So I will give you, go ahead and hit pause and flip back to your identity outline in your toolbox so that we can jot down the ways to factor. Okay, when it comes to factoring, we need to look at the number of terms. There's instances where there are 2, 3, and 4. When it's 2, it can either be guess and check, it can be sum or difference of cubes, or it could be difference of squares. When there are 3 terms, it's usually guess and check. And when there are 4 terms, it's factor by grouping. Now, I feel a little bit bad because back here I said guess and check on 2. And I hope you're recalling that we didn't really say guess and check. When there's 2 terms, what I was thinking was GCF, find the greatest common factor. So that'll just help you. Maybe you need to write out the rules for these on this paper. As you can see, I'm out of room. So I will let you guys write down the rules on your own time. So you can hit pause and go ahead and take a second to write down those formulas. And I'm going to move on to 5.1c. Here we are on 5.1c. The goal for today is to perform the addition or subtraction and use fundamental identities to simplify. If you look up in the upper right-hand corner, today we are going to focus on fractions, everybody's favorite. So looking at problem number A, we're going to add fractions. In that case, we need a common denominator. So the denominator on the left side is 1 plus cosine x, and the denominator on the right is 1 minus cosine x. So we need to multiply this side times 1 minus cosine of x on the top and the bottom. Oops. 1 minus cosine of x. And over on the right side, we would multiply by 1 plus cosine of x on the top and on the bottom. I suggest that you always work left to right and from top to bottom. So I am thinking 1 minus cosine x times 1, I write it down, plus 1 plus cosine x times 1, I distribute the 1 and I get plus 1 plus cosine of x. I have a denominator which I believe that you should not always multiply it out. So for now, I'm going to leave it as 1 minus cosine x, 1 plus cosine x, and it will depend on what my numerator looks like later. Okay, so the first thing that we did was we got a common denominator. The next thing that I need to do is I need to simplify this numerator. So it looks like a cosine of x that's positive goes away with a negative cosine of x, and I have 1 plus 1, which equals 2. At this point, since I have a 2 on the top, I want to think in advance about what's going on in this denominator. Whenever you see things that look like a difference of 2 squares, which is what they are, you should anticipate foiling them out, which would give you 1 minus cosine squared. You should think ahead about the potential of 1 minus cosine squared and how that could be a Pythagorean identity. And the Pythagorean identity would give you something that would be a lot simpler than what you're showing right now. So I am going to FOIL these out and write 1 minus cosine squared x. And then thinking about Pythagorean identities, I know that 1 minus cosine squared x is sine squared x. So this problem that started out as being so complicated, the final answer is 2 times the cosecant squared x, which in calculus, it's a lot easier to work with this problem than it is to work with this one. Go ahead and hit pause and try part B on your own. Okay, hopefully you've had a chance to try part B. I am looking at two fractions that need to be added together, so I am thinking common denominator. One of the things that I am anticipating is that I see secants associated with tangents, and I know that if I can see them as squared things later, then Pythagorean identities will be prevalent. So here we go. This side needs to be multiplied by tangent over tangent. You're multiplying it by 1, it does not change the value. This side needs to be multiplied by 1 plus secant of x. Here we go. Left to right, top to bottom. Tangent times tangent is tangent squared x. Plus, I have some foiling to do. So, 1 times 1 is 1. 1 times secant plus another 1 times secant is 2 secant of x. Then finally, I have secant times secant, which is secant squared x. Divided by, on the bottom, my denominator. Again, I'm not multiplying things out. It is not necessary to distribute unless you think it's going to help you later. Okay, this looks a little bit intimidating, but I see tangents and secants and squared things, and that makes me feel a little bit better. So the first thing I'm going to find up here is a Pythagorean identity, and I'm hoping that there is one. I know that, oh, let's see. So I hit pause and I've been exploring where the Pythagorean identity is up here. I was trying to see if there was a secant squared minus 1, but it's not there. I was trying to see if there was some relationship between tangent squared and secant squared, and it's not there also. The identity actually comes from right here. Tangent squared x plus 1 can be replaced with, I want you to finish my sentence. It can be replaced with secant squared x and leave it like that. So now I have secant squared x plus 2 secant x plus secant squared x, all divided by tangent times 1 plus secant. And I'm anticipating what this is going to do, and I realize that it is good that I did not FOIL these out. And I realize I just wrote a sine when I meant to write a secant. Okay, combining like terms on the top, I have 2 secant squared x plus 2 secant of x over tangent times 1 plus secant. Sitting here to analyze what I've been doing, I am seeing that there's a 1 plus secant on the bottom, and I was really hoping that I could get a 1 plus secant on the top to go away with it. You're always wanting to see if you can simplify further. So up in the top, I see two terms with GCFs, so I am going to factor a GCF. So what comes out of both of these terms? 2 and secant comes out of each one. I'm left with secant plus 1, which is really helpful for what I have on the bottom. This is a nice long problem for us. I have a positive secant plus 1 and a positive secant plus 1. Those can reduce to 1. And I am almost done here after I do some basic identities. 2 times secant is really 2 times 1 over cosine. I'm going to divide that by a tangent, which is sine over cosine. Dividing by fractions is easy as pie. 2 over cosine times cosine over sine. Final answer, 2 divided by sine of x is equivalent to 2 times the cosecant of x. Wow, that was long and involved. Here we go with a couple more problems. Another feature of working in this chapter is to multiply by a well-chosen one. And hopefully you are wondering what the heck I was talking about when I use the phrase well-chosen. Well, like I said, in math you can multiply by 1 anytime you want to because it doesn't change the value. So you can multiply by sine over sine, or 2 over 2, or anything that would maybe help you. So one common thing to do is to multiply a 1 by a 1 that has to do with the conjugate. So if I look at 1 over 1 plus sine, the conjugate of 1 plus sine is 1 minus sine. And the reason why these are helpful in this chapter is because of the Pythagorean identities. I know that the conjugates often give me things that are squared and 1, so it can be a really helpful tool. Again, noticing that this value right here is equal to 1. Here we go. 1 times 1 minus sine is 1 minus the sine of x. On the bottom, I really think that I need to be multiplying this out. So 1 plus sine minus sine squared x. Looking at this, I see that I have something squared, so I'm thinking Pythagorean identity. So 1 minus the sine of x on top divided by 1 minus sine squared x gives you cosine squared x. Now the whole idea was that this is not supposed to be a fraction, and right now it still is. We've multiplied by our conjugate. That didn't solve our problem. Now you guys are going to encounter a thing that we do that's called split the fraction. Very helpful tool. You guys see 2 terms on top and 1 on the bottom. As soon as there's 1 term on the bottom, you can separate the terms on the top. 1 over cosine squared x minus sine over cosine squared x. You guys are mostly familiar with going from this way to this way, because most of the time you've wanted to add fractions together, not move them apart. In this case, we want to move them apart. 1 minus cosine squared, that's a basic identity, secant squared x, minus what do we have here? We have a sine over a cosine squared. So we might want to think of that as sine over cosine times 1 over cosine. Therefore, we're getting rid of those fractions, hopefully. Secant squared x minus tangent of x times secant of x. That's a perfectly acceptable way to leave that. The problem didn't necessarily ask me to factor, but I could factor out a GCF of secant of x. Moving on. Tangent squared over cosecant of x plus 1. So in this case, we see a fraction. We don't want a fraction. It's often helpful to multiply by the conjugate. Go ahead and hit pause and get started on this problem on your own. Hopefully, you know that you're supposed to multiply by cosecant of x minus 1. The well-chosen 1 means that you have to put it on the top also. So I know for sure that I do not want to distribute a tangent times a cosecant. It just seems like it would become more complicated. So tangent squared x times cosecant of x minus 1 over foiling cosecant squared x minus 1. Whenever you see ones and squareds, you look for a Pythagorean identity. In this case, cosecant squared x minus 1 should be able to be changed. I'm just browsing over my sheet. Yeah, cotangent squared. So tangent squared times cosecant of x minus 1 divided by cotangent squared. Again, we need to get this fraction out of here. So basically that means that this thing needs to be manipulated. So really this is tangent squared times tangent squared, because 1 divided by cotangent squared is tangent squared, times cosecant of x minus 1. Final answer, tangent to the 4th power times the cosecant of x minus 1. Nice job. 2 more examples for today. These will look very different than the things that we've been doing. However, you're using this idea of substitution to work with an expression or an equation. It's an expression in this case. It says use the substitution x equals 2 tangent of theta for 0 is less than theta, which is less than pi over 2, to write 4 plus x squared as a trigonometric function of theta. Wow. Here's the goal. This right here is not a trig function. Let's write it down. 4 plus x squared. They're saying replace x squared, or replace the x with this 2 tangent of theta and make it trigonometric. And you'll see why in calculus someday. So I'm going to replace this x. Whenever I replace things, I use a set of parentheses. 2 times tangent theta squared. Now, I'm going to bring into the idea, or bring into this problem the idea that theta has to be in between 0 and pi over 2. The reason why is because we need to keep this quantity under here. You think about what it needs to be. It has to be positive. And tangent of theta is only positive in the first quadrant and the third quadrant. Well, if you think back to learning about inverses, inverse tangent is only allowed on the right side. So we are not even considering problems over here if we were supposed to solve for this tangent. In that case, we are stuck in quadrant 1, which is why we're in between 0 and pi over 2. Here we go, simplifying. 4 plus 2 squared is 4. Tangent squared is tangent squared. Looking at this, I can see that I can factor out a 4 from both terms. 4 times 1 plus tangent squared theta. I'm eager and excited to see a 1 and a tangent squared together because that turns into a Pythagorean identity. I'm going to go ahead and jot down my notes over here. This was factor. This was substitute. 1 plus tangent squared, the Pythagorean identity for that is secant squared theta. And you can square root both of these. The square root of 4 is 2, and the square root of secant squared is secant of theta. It's really important that you put down as a domain restriction that secant of theta has to be greater than 0, and that theta still has to remain in between pi over 2 and 0. Because if it didn't, our original problem started with something that had restrictions. You need to maintain those restrictions throughout the whole problem. Last thing for today. You should find this familiar, and it is a good review. Use the given values to evaluate, if possible, all 6 trig functions. Here you're seeing that cosecant of theta is undefined. So I'm going to write down 1 over sine of theta. You know that that needs to be undefined. Well, in order for that to be undefined, what would sine of theta be equal to? 0. So it is important for me to think, I'm trying to think of the angle where sine of theta is 0. There's another restriction here. Cosine has to be less than 0. For the x values to be less than 0, I'm going to cross off the first and fourth quadrant. So the question is, where is the sine of theta equal to 0 when cosine is less than 0? It's right here at this angle. Hopefully you're referring to theta as pi. So all it wants you to do is evaluate all 6 trig functions at pi. And it's just keeping you in that mindset of thinking. The sine of pi, the y value there, is 0. We just talked about it. The cosine is -1. And the tangent would be 0. 0 divided by -1, which is 0. The cosecant of pi is equal to the reciprocal of this, so it is undefined. The cosine of pi is -1, so the secant of pi would also be -1. And finally, the cotangent of pi is the reciprocal of this one. It would be undefined. All right, guys. It's been another good lesson. Thanks for being here. I'll see you tomorrow.